So thank you, Mike, and for that talk, and thank you everyone for being here today, and for Earl and Nadia for organizing this session. It's a great honor to be here and be talking, and it's great to see everyone here. And I think throughout, as Nafi has already mentioned, and throughout today, you're going to see how TED has impacted so many people in his professional career. So when Earl approached me about giving a talk, and I mainly work in oil and gas exploration these days, but this is a project I worked on a couple years ago, and I thought it might be a little bit more appropriate for TED Madden Symposium, Detectability of 3D sulfide targets, because for much of Ted's professional career, he worked in mining exploration, certainly in his early career was really focused on mining exploration, exploration for sulfides, and had a big impact on this field, and certainly on me. So I'd also like to mention my colleague Don Watts, who also worked with me on this project. So AFMAG stands for audio frequency magnetics. It was a geophysical technique that was introduced by Stan Ward back in 1958 at the SCG meeting, and identifies conductive anomalies from by measuring the tilt angle, the magnetic polarization due to variations in the vertical magnetic field. And its original application was for in the exploration for massive sulfide. So massive sulfide zones are highly mineralized zones, typically very conductive, found in resistive background media. So this was a picture taken out of Stan Ward's first paper, showing a comparison on the right of airborne AFMAG versus at that time standard airborne EM. And I think the idea was that Stan was getting at was that these highly conductive mineralized zones generate very strong vertical magnetic field signatures, and you get very good delineation of the mineralized zones compared to the standard EM. So since then, AFMAG in many variations has been used in mineral exploration, both in airborne and on land. More recently, it was modified by a company called Geotech, where they made measurements of the vertical magnetic field in the air, and then they referenced it to a fixed base station somewhere off on the side of the survey area, and then it's marketed under the name of ZTEM. So the reason we got involved in this project was twofold, really. It was because we had a project looking at it was a mining mineral exploration project in Australia, and we just wanted to understand basically what we could resolve from that. And also, this ZTEM was being marketed quite heavily, and we wanted to understand what you could and couldn't resolve from airborne measurements. Nadia? So a little bit of historical context. In all this, AFMAG or ZTEM or whatever, when you're dealing with vertical magnetic fields, it always comes back to this relationship between the vertical magnetic field and this linear relationship between the horizontal magnetic field. And this was given the name Tipper in a paper by Kiva Vozov in 1972, and I suspect many people here know Kiva Vozov. He worked with Ted Madden at that time. And basically, because it was called the Tipper because it talks about how the horizontal magnetic field is tipped into the vertical. In that paper, Kiva cites Ted Madden as the original source of his idea. And I suspect many of you, I mean, this is perfectly in keeping with Ted Madden, and even today, many of the things I work on, I can go back and most likely the original source of that idea was Ted Madden. And I'm not going to point out every place in here in which Ted has had an impact, but he certainly had a big influence on many aspects of this work. I mean, Earl was asking about the Great Peril, and if you were a TED student, you're very familiar with this very famous paper of Ted's in which he looked at network analogs to geophysical systems. It was totally incomprehensible, like many of his stuff to our students. And I still, but that being said, I still use that in my work. So some of those concepts are still important and relevant, and because it was a very clever and unique and intuitive way at looking at things. All right. So we're going to start very simply, and this is a massive sulfide. This is a 2D massive sulfide model, similar to what one might find in a Canadian geologic environment, where the background is fairly uniform and fairly resistive, electrically resistive. And then you have small mineralized zones. This is dimensions 75 meters wide, 350 meters high, and then at a depth of 250 meters below the surface. They're very conductive. And yeah, so next slide. So and so I'm going to say that this is simply a synthetic modeling study. We're not going to show any data. And so the result for that model is shown here in the top slide, where I've plotted the magnitude of the vertical magnetic transfer function across the profile and as a function of frequency. So high frequency to the top and lower frequency here. And so you see a nice broad response, and you see a change in the sign as you go over the sulfide body. Well, 2D is very simple to code up and to run, but it's not very realistic. The real world, things don't extend for infinity. So in the second slide, I've truncated that, and instead of being infinite strike length, it's now about 500 meters in strike length. And so you can see that the nature and magnitude of the response changes quite dramatically. So the response horizontally becomes much more compact. It's moved upwards in frequency. And also notice a change in scale as I go down. So the color scale is not the same in each of these. So notice that the scale has been reduced by a factor of 10. So just by going from 2D to 3D, you reduced the magnitude of the response by a factor of 10. And this is because in a 3D body, you can't gather enough electrical current in that body to it's like you do in 2D. Okay, so if you take that 3D body and you move it down another half a kilometer, this is what you get. So again, the response is modified, it's broadened, it's pushed down in frequency, but also notice that the amplitude has gone down by another factor of 10. So going from 2D to 3D and then pushing it farther, we've decreased the amplitude by a factor of 100. Well, what might be a reasonable level that we could actually measure in the field? Well, it turns out that for real data, we typically set noise levels. Okay, so I should just mention that these are the amplitude times 100, which is which is commonly referred to as a percent, even though it's not really a percent, but that's how they term it. So for real data, we probably set noise levels anywhere, for extremely good data, maybe 0.1 to 0.3%. So by the time we get to this level, we're really getting at the limits of resolvability for this type of data. Okay, so let's move on to a slightly more complicated model. And this is a similar massive sulfide in a background, very resistive body. But this time we've added two near-surface conductive layers. And this is typical of what one might find in Australia, where there the near surface is covered by these thin conductive layers. Nadia? And so this is just a plot through the strike section. This is the same sulfide body in the resistive background, but now we've got two thin conductive near-surface layers of varying thickness. Yeah, okay, go to the next one. So here I'm plotting the real and imaginary part of the vertical magnetic transfer function across that in the case where there's no conductor. So we just want to see what is the effect of the overburden. And you can see the response in both the real and imaginary part reflects variations in the thickness of that overburden. But notice the level, these are very small amounts. So next slide shows the effect of the contribution due to that sulfide target. In green is just the response due to the sulfide target only. And in blue, in both of these plots, is the overburden plus the target response. I'm sorry?
Oops, that's it.
Oops, well, no, I don't know if it's an oops. It's just you just can't resolve it, unfortunately, because in the best of circumstances, this is sort of our noise level here is about 0.1. Okay. So this summarizes to this point. The blue line is the one resolvable target, the one resolvable response, and this is just for the 3D body in a completely resistive background. The other responses are for the sulfide body in the models where we had the near surface conductive layer. And what happens is when you have near surface conductivity, it's hard to propagate. It's hard to get electromagnetic energy through that. It shields what you see below, unfortunately. You just can't resolve those. Okay, next. Okay, so the final model I wanted to show is something slightly more complicated. And here we're simulating a large sulfide body from the Sullivan ore body in British Columbia. And this is the real topography, and we've simulated, and in this case we're going up, I should have said in those previous models we were looking at ground-based measurements. So in this one we're simulating measurements that would be taken up in an airplane. So this is airborne mode. I've simulated data along each of these flight lines. Next. And so this is a plot of showing the topography and then the massive sulfide body with dimensions 1,000 meters by 2,000 by 100 and a resistivity of 5 ohm meters, and the background is uniform at 1,000 ohm meters. Okay, next. So this is a cross-section through that model showing the topography in the model, the sulfide body. And you see very clearly two things. One, the response of the topography only, even without the target, gives quite a big response. But also, the response with the target gives an equally big response and a different response. And then if you look at the target-only response, okay, so you can see here, this is the target-only response at 3 frequencies, 10, 15, and 25 hertz, and very clearly shows a measurable and resolvable response. So to wrap up, I took that synthetic data and then ran an inversion just to see how well we could resolve it from an inverse method point of view. Took the synthetic data, added random Gaussian noise, ran it through a standard smooth model inversion, and actually we did a good job of resolving the top and the horizontal dimensions of that body. Unfortunately, the typical problem in this sort of inverse problem is it's difficult to resolve the bottom of these conductors. I mean, that's just part of the nature of the business. Okay. So these are my conclusions for this study. The sensitivity to these massive sulfide bodies is limited by the presence of a conductive overburden and by the depth of burial. Spatial wavelengths are large, but we're dealing with plane wave sources. And a large target, similar to the Sullivan ore body in British Columbia, would be resolvable, assuming that the data are reasonable. And of course, there's a lot of issues involved with collecting data in an airborne environment. So I want to, and just finally, again say what an honor it was to be one of Ted's students, and how he impacted all of us, I think, is very clear. And so, thank you very much.
questions? Mike?
So, Randy, given some of these, difficulties, how much is this method used as opposed to other methods for finding these problems?
It's still used. We typically we'll collect not only magnetic field data, but we'll collect electric field data, which also gives us additional information. And this is just a couple problems that trying to resolve small bodies is difficult, even in the best of situations. And then when you complicate it by adding these near-surface conductive layers which shield things, that makes it even more complicated. Of course, no matter what you do in these synthetic studies, you go out into the real world, and the data always is different than what synthetic data show you, and always provide, as you know, provide a new set of challenges to understand. Of course, massive sulfide bodies aren't, we like to represent them as these nice little compact bodies, but the reality is they're much more complicated in the real world. So you could get mineralization over larger zones. I think I picked up a couple, a couple of things I picked up from Ted is I don't publish papers anymore, and I don't give very many talks, and I don't like to talk.